Welcome to our 6th lesson in our series on electromagnetism. In our previous 2 lessons, we explored Michael Faraday's discovery of electromagnetic induction. You should recall that he discovered that when a magnetic field is moved inside a coil, an EMF is induced across the ends of the coil. We can summarize these findings in Faraday's law, which states the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux cutting across a conductor. We also showed that Faraday's law can be expressed mathematically as E equals minus N times delta phi over delta T, where phi equals the magnetic flux B times A. Remember, the minus sign indicates that the direction of the induced EMF is opposite to the rate of change of flux, since the induced EMF opposes the change in magnetic flux according to Lenz's law. Now, in this lesson, we are going to show how the theory of electromagnetic induction is used in transformers. A transformer is used to change the potential difference of a power supply. A transformer is an electrical device that consists of a laminated core of soft iron onto which 2 coils are wound. The first coil is called the primary coil, and the second coil is called the secondary coil. Some transformers can increase or step up the potential difference from a low potential difference in the primary coil to a higher potential difference in the secondary coil. In this case, they are called step-up transformers. Other transformers can step down the potential difference from a large value in the primary coil to a smaller value in the secondary coil. These transformers are called step-down transformers. By the end of this lesson, you should be able to explain how a transformer works by applying Faraday's law, show that there is a relationship between the potential difference in the coils of a transformer and the number of turns, and solve simple transformer problems. Let's have a closer look at the simple transformer in order to find out how transformers work. Here we have a bar made of soft iron connecting 2 coils of insulated copper wire. The primary coil is connected to a switch and a 12-volt battery. The secondary coil is only connected to a center zero galvanometer and not to the power supply. Watch carefully what happens to the needle of the galvanometer when I close the switch, allowing the current to pass through the primary coil. Did you see that the needle of the galvanometer moved for an instant and then returned to 0? This shows us that an EMF was induced in the secondary coil for a very short time. Let's take it slowly and think about what happened here and how the EMF was induced in the secondary coil. When the switch is closed, current starts passing through the primary coil. Remember, a current passing through a coil will produce a magnetic field. This magnetic field will magnetize the soft iron core that passes through both coils of the transformer. So a magnetic field builds up around the transformer. This means that the magnetic flux changes from 0 when the switch was off to a maximum value just after the switch was closed. Remember, a change of magnetic flux in a time interval is called the rate of change of magnetic flux. From Faraday's law, we know that the rate of change of magnetic flux cutting across the coil results in an induced EMF being applied across the coil. So Faraday's law explains why there is an EMF induced in the secondary coil when the switch was closed. Notice that the reading on the galvanometer did not last for long, but returned to zero, even though the primary coil was still connected to the 12-volt battery. Can you explain why this happened? Well, when the current in the primary coil reached a constant steady rate of flow of charge, the magnetic field set up by this current surrounding the transformer also remains constant. Because it is constant, this means that there is no longer any rate of change of magnetic flux cutting across the secondary coil. So there will be no EMF induced in the secondary coil. As a result, the needle of the galvanometer returned to zero. Can you predict what will happen when the switch is opened? Watch and see. Did you see how the needle of the center zero galvanometer jumped in the opposite direction for an instant and then returned to zero? This shows us that an EMF was induced in the secondary coil, but it was induced in the opposite direction from when the switch was closed. Can you explain why an EMF was induced when the switch was opened? Let's go through the process together. When the switch was opened, the current in the primary coil dropped to zero, and the magnetic field associated with it also decayed and died away. So the magnetic field cutting across the secondary coil changed in a very small time interval. This means that there was a rate of change of magnetic flux in the secondary coil, and as a result, an EMF is induced in the secondary coil. Can you see that only when we opened or closed the switch did we induce an EMF in the secondary coil? When there was a constant supply of current to the primary coil, no EMF was induced in the secondary coil. So if we want to get a continuous EMF in the secondary coil, we could continually open and close the switch connecting the primary coil to the battery. But this is not very practical. A more practical way of doing this is to supply the primary coil with a current which changes its magnitude and direction at regular intervals. This type of current is called alternating current, AC. This is what we use when we plug into a mains power supply. Let's watch what happens to the galvanometer readings when we connect the primary coil of the transformer to an AC power supply. Look, the needle of the galvanometer connected to the secondary coil vibrates rapidly, indicating that a changing potential difference has been induced in the secondary coil. Notice that the induced EMF is not constant, and so the induced current in the secondary coil will be an alternating current too. Now let's apply Faraday's law to each of the coils of the transformers in turn to derive a relationship between the EMF and the number of turns or windings on each coil. Let's start with the primary coil. When the power supply is switched on, an EMF V subscript P is set up across the ends of the coil. As a result, a current passes through the coil which sets up a changing magnetic field around the coil. According to Faraday's law, the magnitude of this rate of change of magnetic flux is directly proportional to the EMF Vp applied across the ends of the coil. In this primary coil, we use symbol N subscript P to indicate the number of turns or windings in the coil, and so can rewrite Faraday's law equation, especially for the primary coil, as Vp equals Np times delta phi over delta T. Now have another look at the transformer apparatus. Notice the coils are connected by the laminated soft iron core. We know that soft iron is a magnetic material, which means that when it is placed in a magnetic field, it is magnetized by the field. However, when the iron is removed from the magnetic field, it is no longer magnetic. So in any transformer, the soft iron core links the magnetic field formed in one coil to the other coil. Any change in magnetic flux in one coil will be carried by the iron core to the other coil. Now, with this in mind, let's write an expression for the EMF induced in the secondary coil using Faraday's law. Here, we use the symbol V subscript S for the EMF in the secondary coil, and N subscript S for the number of turns or windings on the secondary coil. This gives us the equation Vs equals to Ns times delta phi over delta T. Now we can divide each equation by the number of turns to get an expression for the rate of change of magnetic flux. But remember that the rate of change of magnetic flux cutting through the primary coil is exactly the same as the rate of change of magnetic flux cutting through the secondary coil. So we can join these two equations to get a very interesting relationship between the EMF and the number of turns or windings in each of the coils of a transformer. We can use this ratio to complete simple transformer calculations for both step-up and step-down transformers. Have a look at this example and see if you can solve it. There are 20 turns in the primary coil of a step-up transformer, which transforms 5 volts to 220 volts. How many turns are there in the secondary coil? Compare your answer to mine. Here I have written down the given information and the equation I will use. We need to find Ns, so let's make it the subject of the formula. We multiply both sides of the equation by Ns and Np, and then divide through by Vp. Then we substitute the values into the formula. Np is 20, Vs is 220 volts, and Vp is 5 volts, and we find that Ns equals 880. So there will be 880 turns or windings in the secondary coil. Now, we don't study transformers just to understand theory and to use equations to solve problems. To learn a bit more about the practical functions of transformers, we went to speak to Donnie LaRue, who is a senior communications practitioner at Eskom Generation.
We generate electricity at our power stations at a very high voltage. Our voltage is electrical push to push the power down the line. We also know it as potential difference. Why do we generate at such high voltage? We generate high voltage to enable us to eventually transmit this electricity over vast distances. How do we do it? First of all, we go into a transformer. At power stations, we can step the voltage up from 20,000 volts to 275,000 volts, 400,000, and even 765,000 volts. What happens? The moment you step the voltage up, the current flow drops. If the current flow drops, we reduce the potential for generating heat. We can use a thin conductor made of copper and aluminium that can conduct electricity efficiently and effectively over vast distances. With a lower voltage, higher current, you have to use a robust conductor. So we cannot afford to use that to transmit electricity over vast distances. So from this power transmission network, the electricity is distributed over the length and breadth of South Africa. It eventually links into substations. Now, substations, again, the opposite happens to what happened at the power station. At the power station, we step voltage up. At the substation, we use transformers to step it down. We step the voltage down to voltage required by a specific user. Say, for instance, it's a nearby town. So we step down from 275,000 volt to 88,000 volt. It goes from the substation to a distribution substation at that particular town. There again, we step the voltage even down to a lower voltage so we can use it in our homes at 220 volts. So you can see it was quite an eventful road for the power to leave a power station to eventually get to our homes. In the process of transmitting electricity and transforming electricity from one voltage to another, it's not 100% efficient. We lose some energy. We lose energy on the lines, but we also lose energy in the transformer. In other words, stepping up or down, or stepping down and up. What happens is that your iron core in the transformer is laminated and glued together, and therefore in doing so we limit the amount of heat generated, and subsequently the losses are less.
It is always really interesting to see the real-world applications for the theory we learn in these sessions. Let's look at another practical application. Here is a cell phone charger. This charger has a step-down transformer inside it, which steps down the voltage from 220 volts from the mains to 4 volts. Even though this is a small transformer, you will notice they get hot when in use. For your task, I want you to solve a transformer problem based on the working of a cell phone charger like this one. A cell phone charger has a small transformer with 20 turns wrapped around the secondary coil. The transformer steps down the potential difference from 220 volts to 4 volts. Calculate the number of turns on the primary coil. In our final lesson in this series, we will examine what happens when charged particles move through a magnetic field by finding out how a television works. Until then,
Yeah.